Now we have some sample problems related to acceleration to work. The first one's going to start from a story of my babysitting days. So I used to babysit twin girls. They were actually my grad school advisor's daughters. They're fantastic. But like a lot of pairs of siblings, they occasionally fought. And one day, one of the girls decided to push her sister and the tricycle she was on towards a wall. Okay, I didn't actually measure the initial speed and anything like that, but if, say I had, and the initial speed was 5 meters per second, and the wall was 10 meters away, I'm trying to figure out if the child is going to hit the wall. So in this case, we'll pretend the tricycle had a flat tire, and it was slowing the tricycle down at a rate of 1 meter per second squared. So we want to know, did the tricycle and the child hit the wall? I know, you can barely wait to figure out if the tricycle is going to hit the wall. So here's what's known. We know that the initial speed was 5 meters per second. And we sort of have a setup of what this problem might look like here on the right. So there's the kid. We're just going to represent her with a smiley face. And the wall is 10 meters away. If you remember, I said you can let anything be positive. So for the sake of this problem, I'm going to let to the left be positive and to the right be negative. So the initial velocity is 5 meters per second in the positive direction. This confuses people some. I don't really know what the final v is going to be, right? Because I don't know if the child's going to hit the wall and be stopped, in which case I know it would become 0, but the acceleration isn't constant once that kid hits the wall. If anybody's ever run into a wall, you'll notice that you slow down a lot faster suddenly. I do know that the initial constant acceleration and the acceleration for the part of this movement that has constant acceleration is negative 1 meter per second squared. So remember I said to the right is going to be negative. I know that the initial velocity is 5 meters per second, and I know that the flat tire is slowing down the tricycle. So I know that the acceleration has to be in the opposite direction of the velocity. So I'm going to make it negative 1 meter per second squared. I don't know how long this occurs, and I actually don't know the distance because I could try to figure out how fast the kid might be going at 10 meters, but I'm not sure that the kid's going to go a whole 10 meters with this tricycle with a flat tire. So right now I have too many unknowns. So I'm going to make a decision. I'm going to say I want to figure out how far the kid and the tricycle are going to go before v equals 0 meters per second. If my kid here would go more than 10 meters before stopping based on this constant negative 1 meter per second squared acceleration, then I know the kid is going to hit the wall. If not, if v equals 0 meters per second when the displacement is only 8 meters or any number less than 10, then I know the kid isn't going to hit the wall. So now I want to figure out what equation I want to use and how I want to work this. So I've decided that I'm going to let v be 0 meters per second. I have a v sub 0 and I have an acceleration. So I want to find displacement. So this equation has everything I need. So I'm going to choose this equation. I'm then going to substitute in the values that I already figured out. So I said I want to figure out when v equals 0. So the position where the child would stop just due to the flat tire. So I've substituted that in here. I then want to figure out v sub 0. The initial velocity was 5 meters per second. So I have that here. And you'll notice I've gone ahead and squared both of those, which is why my new units are meters squared divided by seconds squared, plus 2 times the acceleration times the displacement, which is what I want to find. I do a little bit of rearranging of the equation, and I'm able to solve that the child would go 12.5 meters before the flat tire would stop her. That means, yes, the child hits the wall. Okay, Now we have one that you're going to work some of. So a car initially at rest travels 20 meters in 4 seconds along a straight line with constant acceleration. We want to figure out what the acceleration of the car is. Which answer represents the variables we know for this problem? And there are 3 of them that we know. 2 are given pretty directly. 1 you kind of have to read a little bit more closely. So we know this is a constant acceleration problem because we said the acceleration was constant. So we can look at all these equations that describe motion with constant acceleration to find a way to calculate the answer. So this is what we know. We know the displacement, we know the time, and because the car was initially at rest, we know that the initial velocity was 0 meters per second. If we look at our equations for constant acceleration, let's look and see where we can find these. We also want to think about, what do we want to know? We want to find acceleration. So we want an equation that has displacement, time, initial velocity, and acceleration. That one looks like it'll fit the bill. Using this information, what was the acceleration of the car? Now we're going to think a little bit about free fall, which remember is just constant acceleration. It's just that we know that the acceleration will always be negative 9.8 meters per second squared. So skydivers use parachutes to create drag and prevent them from falling and accelerating at negative 9.8 meters per second squared, because that would be very bad. So we want to figure out how long it would take a skydiver to reach the ground if he or she jumped from 3,650 meters in free fall. So no parachute and accelerating at negative 9.8 meters per second squared. We also then want to figure out how fast he or she would be going just before hitting the ground. I say just before hitting the ground because, again, we know that if this unfortunate situation occurred, the ground would stop the skydiver. So we want to say just before that moment of contact. So again, we want to think about what variables we know. I'm going to give one little hint in that you can assume that the initial velocity equals 0 meters per second. We'll get into this a little bit more later on and why we can make that assumption and still have this equation work, because we know the skydiver's probably in a plane and that's moving at some speed, but I promise I'll explain that more. In this case, you can assume the initial velocity is 0 meters per second. So for this problem, we know the initial velocity, we know the displacement, and we know the acceleration. So now we want to figure out which equation we can use given those variables to find time. So we need an equation that has displacement, initial velocity, time, and acceleration. Because again, this is free fall, so we know that acceleration will be negative 9.8 meters per second squared. Now that we have our variables and our equation, we're going to do a little bit of plugging and chugging. One thing that's really important to remember here are your positives and negatives. We said that the acceleration was negative 9.8 meters per second squared. If we take down to be negative and up to be positive, as we are by saying it's negative 9.8 meters per second squared, the skydiver starts at 3,650 meters and ends at 0 meters. So is that displacement positive or negative? Now that we have the time, we can look through our constant acceleration equations and figure out how fast the skydiver would be going when he or she hits the ground. Just so you know, 267 meters per second, which should be about what you got for that last question, is about 600 miles per hour, which is roughly how fast a Boeing 747 flies, sort of at cruising speed. Don't jump out of airplanes without a parachute. Just a general life knowledge right there. So, at a stoplight, a truck traveling at 15 meters per second passes a car as the car starts from rest. So the truck is going 15 meters per second, the car is at rest. The truck travels at constant velocity and the car accelerates at 3 meters per second squared. How much time does the car take to catch up with the truck? So first, we need to figure out kind of what we need to solve for. So the car catches the truck when their blanks are the same. Do they need to be going the same velocity? Do they need to have the same acceleration? Does it need to be the same speed? What needs to be the same for the car to catch the truck? So we know that the car catches the truck when they're in the same position at the same time. So that means they'd have the same displacement if we let our time t equals 0 right at the stoplight. So knowing that, we want to figure out which equation represents the displacement of the truck. So we have the truck traveling at 15 meters per second. We said it's at a constant velocity. So what does that mean about its acceleration? And try to find which equation could be the displacement of the truck. Now you want to figure out which equation could represent the displacement of the car. We know that the car started from rest and has an acceleration, a constant acceleration of 3 meters per second squared. So which could represent the displacement of the car? Now that we have those two equations, we need to combine them to get one equation so that we can solve for time. Which of the equations below could be the combination of these two equations? Now we want to take those equations and do a little plugging and chugging and solve for the time at which the car catches up to the truck. Now that you have an answer, it's best to check it. So figure out what's the position of the car at that time t that you just calculated. Now figure out the position of the truck at that same time t. This should be the same position you calculated for the car. Rounding might make them a little bit different, but you should get essentially the same number.